everyone, I am V. Soumyashri from CSIT. Today I am here to discuss about from federated to fog learning, distributed machine learning over heterogeneous wireless networks from the course Principles of Artificial Intelligence. Introduction. Overview. Distributed machine learning (DML) involves training machine learning models across multiple devices or servers instead of centralizing the data in a single location. Key aspects of this distributed machine learning is parallelism. DML allows data to be processed simultaneously across multiple devices, increasing computational power. Data privacy. By processing data locally, DML minimizes the need to centralize the sensitive information. Use cases suitable for large data sets that can't be easily transferred, such as IoT applications, cloud computing, and mobile networks. The challenges in DML are latency, delays in data synchronization across devices, heterogeneity, handling diverse device capabilities and network conditions, model consistency, ensuring that updates across devices are coherent and accurate. Federated learning overview. Definition of federated learning. FL is a form of DML where multiple devices collaboratively train a model while keeping the data local. How it works. Devices, for example, mobile phones, IoT devices, compute local updates on a shared model and send only model updates to a central server. Advantages of FL are data privacy. Raw data remains on the local devices, reducing the data privacy concerns. Decentralized training suitable for organizations with distributed data, such as hospitals or financial institutions. Limitations of FL are high communication costs. Repeated model updates consume significant network bandwidth. Security challenges. Potential exposure to malicious updates from compromised devices. Model consistency. Synchronizing model updates across multiple devices can lead to inconsistencies. Introduction to fog computing. Fog computing extends cloud computing to the network edge, bringing data storage and computation closer to data sources like sensors, IoT devices. The key features of fog computing are edge data processing. Data can be processed locally, reducing the load on the central cloud. Low latency. Applications, especially in IoT, benefit from faster processing. Importance critical for latency sensitive applications in industries such as healthcare, transportation, and manufacturing, where data needs to be processed quickly. Fog learning and its advantages. Definition and architecture. Fog learning distributes ML tasks across edge devices and intermediate fog nodes. Unlike FL, it leverages local and intermediate nodes to process and analyze data before sending it to the cloud. Benefits of reduced latency are fog nodes process data locally, enabling near real time response. Data privacy. Sensitive data can remain within the local network. Network efficiency. Offloading computation to fog nodes reduces the bandwidth usage. Use cases. Applications include real time health monitoring, remote machine diagnostics, and real time video analytics. Comparison between federated and fog learning. Architecture differences. Federated learning uses centralized coordination, example server, to aggregate model updates. Fog learning employs a multi layered approach, often involving localized processing. Data management. Federated learning. Data remains entirely on local devices. Fog learning Data may be processed at both the edge and intermediate layers with selective and data sharing. Efficiency: federated learning can be resource intensive with high network demands. Fog learning, more efficient energy, particularly suitable for IoT applications requiring quick data analysis. Distributed learning over heterogeneous wireless networks. Challenges are resource heterogeneity. That means devices in a network have varying computational power, memory, and battery life. Network topologies. Wireless networks vary in range, reliability, and speed. Dynamic conditions. Devices frequently connect and disconnect, causing intermediate availability. Adaptability. Model updates. Models need to adopt the both high-end and low-end devices. Network load balancing. Effective load balancing ensures that devices are not overwhelmed. It means that the not devices are being so many. Optimization needs efficient protocols to handle device churn, energy efficient algorithms, and load balancing techniques. And the key technologies enabling fog and federated learning are edge AI hardware. Specialized hardware like NVIDIA Jetson, Intel, and Google Coral for edge computing. Communication protocols. High speed protocols like 5G, 556, and low power wide area networks for robust connectivity. Security protocols. Privacy preserving methods such as homomorphic encryption and secure multi party computation. Blockchain for trust and security in distributed systems. Applications of federated and fog learning. Smart cities, predictive traffic control, pollution monitoring, and public safety. Healthcare. Data from medical devices can be processed in real time for alerts and diagnostics without leaving the healthcare provider's network. Autonomous vehicles. Edge devices within vehicles process data locally for quick decision making, while fog nodes aggregate data for broader analysis. Challenges in federated and fog learning. Security risks. Data leakage. Sensitive data could be exposed if updates are intercepted. Poisoning attacks. Malicious devices could inject harmful updates. Scalability issues. With an increasing number of devices, coordinating model updates becomes complex. Data heterogeneity. Different data types and formats from varying devices make training models uniformly challenging. Case studies and research developments. Case study 1: Smart healthcare monitoring with fog learning uses wearable health devices to monitor patient vitals with fog nodes processing and analyzing data locally for early alert systems. Case study 2: Autonomous vehicle federated learning enables vehicles to share insights without disclosing raw data, thus enhancing object detection and decision making. Research developments, emerging algorithms for efficient distributed learning, privacy enhanced protocols, and advances in edge AI hardware. Future directions in distributed machine learning. Enhanced protocols, new low latency protocols are under development to support real time learning in edge environments. Hybrid models, combining federated and fog learning for enhanced flexibility, using federated updates while utilizing fog nodes for pre-processing. AI driven optimization, AI based techniques for resource management, adaptive learning rates, and power efficient models tailored to each edge device. Foundation of federated learning. Core principles: Data remains local, model updates are shared instead of raw data. How federated learning works. Each device trains a local model. Models are then aggregated to improve the global model. Illustrative examples. Examples such as Google Gboard keyboard. Predictive text training without uploading user typing data. Fog learning architecture and design. Multi-tier structure, explanation of edge, fog and cloud layers in fog computing. Data flow, how data is processed initially at the edge, refined at the fog layer and stored or further analyzed in the cloud. Processing advantages, reduces the latency and minimizes the data transit through centralized servers. Challenges in data privacy and security. Threats in distributed system, risks like model inversion attacks, data breaches and poisoning. Data privacy techniques, differential privacy, secure aggregation protocols and homomorphic encryption. Legal compliance, how distributed learning can assist with compliance to regulations like GDPR by minimizing the data movement. Conclusion, we explore the roles of federated and log learning in enabling distributed machine learning, especially in heterogeneous wireless networks. Each framework brings unique benefits. Federated learning excels in privacy by keeping the data on device, while fog learning reduces the latency and enables real-time processing by leveraging edge resources. Real world impact, it has many real world impacts and also challenges and solutions for that. The future outlook, the integration of 5G, edge AI hardware and hybrid learning models points to a future where distributed machine learning can scale globally, driving innovation in IoT and intelligent systems. The final thoughts are federated and fog learning represent significant shifts in machine learning architecture, paving the way for a more inclusive, efficient, and adaptable AI landscape across industries and communities. Thank you for giving this opportunity.